In the previous video, we talked to the first author of SwAV method. In this video, I'm going to delve into the detailed explanation of the loss function used in SwAV.
This is your standard cross-entropy loss function. For self-supervised learning papers like simclr, this is what you plug your values into. This is the standard simclr loss where zi and zj are views of the same image. And then you have a bunch of negative samples in the denominator. You take the log of this and you sum over the negative log values of this loss function when you are reducing the loss for simclr. Q from the cross entropy term is either set to 0 or 1. 1 in the cases where these zi and zj are views of the same image, and 0 in other cases. Now this is what you have in SwAV. Let's call the views of a single image as S and T, and Zs and Zt are the output of a network. You have a batch size of B, and now you have k prototype vectors C1 to Ck. We use the similar cross-entropy loss function in SwAV, but the formulation is quite different from simclr. Let's take an example of how this loss function is formulated for SwAV. Say you have two prototype vectors in this example, and a batch size of 3. All of these z's are for a single view T. Z1 is closest to C1, while Z2 and Z3 are closer to C2. To compute how similar each of these representations are to the prototype vectors, you compute Z transpose C, a matrix multiplication which gives you this matrix. Now, to compute the probability PTK, which here is defined by how similar the representation Zt is to the prototype vector Ck, you take this. You have a fixed number of samples in the denominator. Since you're not doing any negative sample, you have a fixed number of prototype vectors. And this provides how similar Zt is to Zk. Now, this is where the difference starts from, say, simclr. You're not computing the similarity between two views of the same image, but rather between a single representation and the prototype vector. Now, the QS here is supplied by the other view and not this view. So in the case of simclr, when two views, say you had similar views of the same image, Zi and Zj, this Q would have been 1. But that's not the case with SwAV. First of all, Qs are not limited to binary values of 0 and 1. Q can be continuous between Q can continuously take any value between 0 and 1. And second of all, the idea is to see if this can predict the cluster assignment of the other view of the same image. So basically, if Zt from an image can predict the cluster assignment of Zs, and that's why Qs, or the target variable of the cross-entropy loss, is supplied by the other view. So combining these ideas together, we use Zt to predict the assignment of the other view, and hence Qs, and we use Zs to predict the other assignment Qt. And these are the two cross-entropy loss formulations. You have a summation over Qs log of Pt and Qt log of Ps. You add these two loss functions together to get the SwAV loss. We just looked at the loss formulation of SwAV. Now in SwAV's cross-entropy loss function, the Q term comes from the second view, while the P term comes from the first view. So the question is, how is this Q computed? Because clearly Q is not just a bunch of 0 and 1 values. 0 being for the general case, and 1 where, say, a Z representation is closest to its prototype vector. Q actually takes continuous value between 0 and 1, and this is the loss function which they optimize or maximize in this case in order to attain the Q values. This is basically a trace over Q transpose C transpose Z, and the second term acts as a regularizer. Here, H defines the entropy of the Q matrix. Now, in order to compute this Q transpose C transpose Z, we first show you C transpose Z in our toy example. And this is the output that we get. with, say, 2 prototype vectors and a batch size of 3. And let's just assume that we are doing this for the tth view in our setting. So, and by the way, these are like the Q being computed here is for T. And this Q after this computation process will be used in the cross entropy for the S view. So let's just assume we have like a bunch of these values in our Q matrix. We got our C transpose Z. We take this Q matrix, and this is a transpose. We take the transpose of the Q matrix and multiply it with C transpose Z and take the trace. Since we chose like prototype vectors and the representations of the TF view in our previous example in such a way that C1 was close to Z1 and Z2 and Z3 were close to C2. So these dot products will take a bigger value in this whole equation. And hence, when you are trying to maximize the values of Q, these individual elements of the Q matrix should take a bigger value in order to maximize this whole thing. Now, this is where the second part makes this whole equation interesting, or the regularization term or the entropy term. The entropy term is simply a summation over, like a negative summation over Qij log Qij, or basically doing an entropy over each of these individual elements. Now, if we take a look at the log function here, all of these Q values are between 0 and 1. So anyway, this term overall adds positive weight to this whole maximization. And the bigger this regularization term is, the bigger this whole equation would be, and hence it's beneficial overall. Now, if we look at the values that this can take, if Q takes a really small value, we get like the log Q term would be quite large, but it would be multiplied by a really small coefficient. And hence overall, it's still a smaller value. If Q takes like a value closer to 1 here, this term would be large, the coefficient itself, but the log value would be really close to 0. And hence that's also not beneficial in maximizing. Say we would get the optimum somewhere in the middle, and hence each Q taking a value in the middle is optimum for this thing. Like the regularization term overall would be maximized if each Q takes an optimum value somewhere in the middle here. And that's why this regularization term or this entropy term kind of maximizes as each value of Q becomes more homogeneous in the Q matrix. So that's what the whole regularization term adds to this equation. Even though you are trying to maximize the value of Q where this Ci is closer to Zj, or basically a representation is closer to a prototype vector, at the same time, you have a regularization term which also creates a more homogeneous matrix. So that's the idea of distributing Q and not just concentrating Q to zeros and ones in the cross entropy term for SwAV. Now we think about how do we actually solve this maximization problem and get the optimal Q matrix. The SwAV paper rewrites that equation as this and converts it into an optimal transport problem. So what does this say basically? First of all, Q is a K cross P matrix with positive values, and then you have these constraints where the row sum, like if you sum over, if you take the sum for each row, you would get 1 by K, and if you take the sum over each column, then you'll get 1 by B. So this is basically giving you this for Q. And now the question is, why does this constraint create a more homogeneous matrix, or why does this constraint uphold the regularization term from the previous thing? And this is kind of the intuition behind it. Say you have like prototypes listed here, like each row is a is for the prototype. So you have C1 and then you have CK, you have a K cross B matrix. As you sum over all the batch elements, each prototype gets 1 by K as its value, and hence it's equally likely to be chosen. And the same thing applies over the batch. So both these constraints equate to the fact that each prototype is picked B by K times in a batch of size B with K prototypes. And with this ratio, you can see that this is a homogeneous selection of prototypes and thus a more homogeneous Q matrix, basically. And that is how it synchronizes with the regularization term in the previous equation. We now take a look at how do we actually solve this optimization for Q using the sinkhorn algorithm. We initialize our Q with C transpose Z. That's our cost function. And that kind of creates the whole thing where you assign bigger Q values to the dot products where CK, like the kth prototype vector, is closer to, say, ZT. And that's where you assign the major weights. And that's what creates the maximum value for the trace term that we saw in the first equation. As you iterate over this, for each iteration, you scale the rows so that they sum to 1 by K, and you scale the columns so that they sum to 1 by B. You take away some weight from the bigger values of Q and redistribute them to make the whole matrix more homogeneous. And that's what this iterative algorithm for sinkhorn does. And that's how solving Q, like getting the optimal Q using the sinkhorn algorithm, maximizes the initial equation that we saw with the trace and the regularization term, which was basically the entropy. And now, since we have obtained the optimal Q matrix for the Tth view, we will use this Q matrix and apply it to the cross entropy function of P, the other view, basically, PS